All right, so this is the last session of HoTT, and our first talk is by Hart on left adjoints and colimits.
Thanks. Yeah, I'll be talking exactly as the title says on the interaction between left adjoints and colimits. Warning, I'm not developing a lot of new machinery, but I think it's a cute story and it should be useful. Okay, so the goals first in general to see whether left adjoints always preserve colimits in wild categories, which is the setting for category theory in this talk. We'll see that it doesn't always hold, but we'll find a reasonably nice sufficient condition for it to hold. And then we'll apply this condition to a prominent example of a left adjoint HoTT, the suspension functor. And to get especially the mechanization to go through, also the paper proof if you want, it turns out to make it feasible in book HoTT, I needed to develop a little extension of what's called Cavallo's trick, and we'll look at that too. All right, so why did we start looking at this? I mean, the preservation by left adjoints of colimits is probably uncontroversial in its importance, but in our case, I originally wanted to just show what I thought was a little corollary of some work on colimits and coslices of a universe, which is that pointed colimits always preserve acyclic types, which are types whose suspension is trivial. And all I needed as the remaining piece was that suspension preserves colimits. And as I started to work it out, this is how this story came about. Other things was, for me, was constructing colimits in various wild categories of higher groups by making them into appropriate reflective subcategories. That's another reason why I needed preservation theorem. And then something that I haven't done but could be useful is that a simple preservation lemma like this would actually greatly simplify the construction of homology theory as described by Graham in terms of stable homotopy theory. Stable homotopy groups. Okay. So let's just replay the classical proof. I'm going to call this the standard proof. It's not the only well-known proof in a one category theory textbook, but I think it probably is the most popular and the one that, as you would read in our abstract, I think is the best to try to port into wild category theory. So consider a diagram valued in a category C, any normal classical category C. Let's say it has a colimit. I'll just label it by T. And we had this short and sweet chain of isomorphisms, natural in both variables. Writing this down alone isn't enough. We need to prove that this chain, the composite chain, is equal to the canonical post-composition function. Not a problem in classical settings, but as you might expect for those who have played with wild categories, this part, the equality with the post-composition functions where things can break down. Okay, so let's recall some wild category theory. A wild category, just take the definition of a pre-category from the HoTT book, but just remove the assumption that those Hom types are zero truncated. Okay, so the idea is we postulate all this one categorical data, but we're purposely leaving it completely incoherent by not having any truncation on the Homs. So let's suppose that we have L and R again, this time inside HoTT. They're one coherent functors or wild categories. So they have the axioms for preserving composition and identity if you want, but no higher coherences on those. So let's suppose that there's an adjunction inside HoTT. I'm translating the standard Hom isomorphism naturality square definition. So we have a family of Hom equivalences, and then we have a family of proofs that witness the naturality squares in each variable. For this talk, since we're just focusing on left adjoints, it turns out that we actually never need to use V1. So if you just want to think of one naturality square, that's fine. We're going to look at free categories as our analog of diagrams inside HoTT because we have that whole semi-simplicial type infinite tower of coherence problem. So we're going to take a graph, which is a type of vertices and a family of edges between vertices. consider the natural notion of a diagram on that graph in a wild category C, consider a cocone on, let's call an object, a cocone on an object, let's call it T and C, under the diagram F, and let's suppose that this constitutes a colimit, meaning that, just porting the definition to wild categories, that the post-composition function is an equivalence. So we can replay the chain of isomorphisms pretty much no problem again. The only thing I want to note this time is let's think of that final type at the end of the chain as the type of cocones on Y, this time under the induced diagram obtained by L in D. And now we want to think, is this chain equal to the post-composition function? It's not. In the abstract, I give a small counterexample based on the H-space structure of S1. It's not long to describe. But the problem is that the legs of when you apply when you take the value of each of the two functions, the output, and you look at the output, the legs of each of the output cocones are equal, but the commuting triangles, the homotopies witnessing those, are not necessarily equal. Okay, so let's look at what a sufficient addition would look like to get this standard proof to go through in the wild category setting. Our definition of adjunction, when you look at it, it's fine for one categories because all the higher equalities that we would need to prove just go away. They're trivially satisfied, but it's not coherent enough for wild categories, at least when we try to prove this property. In particular, we have nothing about the interaction in the definition between the naturality squares, or just square in this particular setting, and the equational axioms that hold for the wild categories and for the wild functors, in particular the identity that witnesses that L preserves composition. So the idea is that getting this proof to go through, meaning that getting those two functions to be equal, amounts to a condition on this interaction between these two things. And here it is. It's just a bunch of fun with half adjoint equivalence, equational reasoning, and homotopy naturality, and some other stuff. But simple ingredients from the Hart book. This is all mechanized, by the way, so I shouldn't have made a mistake. And we're going to call the condition two coherence, and we say that the left adjoint L is two coherent if this six-sided diagram commutes. Without looking too deeply into the actual terms, you'll just notice that it's a condition on the interaction between these V2s, which is the naturality square term, some associativity terms in the wild categories, and then on the side, on your bottom left would be this L circ, which is the composition law for L. The one thing I'll say about this is actually, I think, reasonable and actually quite short, given the other formulations that come out of the proof I did of the equational reasoning. So I think this is the prettiest form I got it to, and therefore potentially the most useful. As I said, it's equivalent to getting the proof to go through. So in particular, if L satisfies this two coherence condition, then the induced cocone in D is colimiting, meaning that L preserves colimits in this case. So let's see if it actually applies in practice to things we care about. In particular, we have this left adjoint, the suspension functor from the category of pointed types to the category of pointed types. We want to show that it's two coherent as a left adjoint to omega. Using the structure identity principle, this two coherence turns into a homotopy between pointed homotopies, between pointed homotopies actually. And I make this precise in this definition. A homotopy between pointed homotopies for us is a homotopy between the underlying homotopies, and then a dependent path over that homotopy between the underlying homotopies. Okay, so that's what we need to construct to prove suspension is two-coherent, is we need to give one of these higher homotopies. So when doing this in AGDA, and then getting to the case of suspension functor in particular, constructing this homotopy between the underlying homotopies, mu it's messy, but I wouldn't say it's unusual. It's doable. Ultimately, it's fine. The dependent path actually turns out to be horrible. When the gold term that's generated by AGDA is horrific, and I didn't want any part of it. So I tried to think of ways to avoid it. And then the trick to avoid it in this case is notice that we're landing in a loop space when we're constructing these homotopies. So going back, when we're proving this coherence, things will end up in an object where the right adjoint's applied, and the right adjoint in this case is omega. So since it's landing in a loop space, we can apply some properties of what's called homogeneous types, which have been used a lot in the past in other examples. We need it to be strongly homogeneous. It's just a small coherence condition on the definition. And the lemma, which is yet another Cavallo's trick, because this trick has seen different forms, including Axel's proof of the symmetric monoidal structure of the smash product. So here I'm promoting it to one higher dimension. So it says that if we're landing in a strongly homogeneous type, and we have two pointed homotopies between pointed functions that are going into that homogeneous type, then as long as we have a homotopy between the underlying homotopies, then those two pointed homotopies are homotopic. So all we need is that underlying homotopy. Homotopy between the underlying homotopies, and we're done. And as I said, we constructed it. It was doable. So now we can just ignore the dependent path. Okay. So that's actually it. That's the whole story. But this does bring up some questions. First, this trick for the suspension was very unique, very specific to this setting. We were landing in omega, in a loop space. The general situation with the smash product is not so lucky. So that gold term that I ran away from is actually going to be even worse in the smash product case. So I'm curious if there's something we can do to get it through in a book hot mechanization. Other things is we can without too much problem show all modalities on U satisfy two coherence, so the preserved colimits. You also wonder from that whether all reflective subuniverses of U satisfy two coherence. And if you think of what I did as reflecting colimits back to a subcategory through a left adjoint as the usual way to prove that a reflective subcategory inherits colimits, then this quote from the Hart book, to me at least, doesn't seem so obvious at this point, because the two coherence of an arbitrary reflective subuniverse seems trickier. So it made me question this quote, which said that everything can go through in a visible way. Okay. So the very last thing is the conclusion, which is that we have a formalized proof that left adjoints preserve colimits under a reasonable condition, and that the suspension functor satisfies it. And then here's a link to the AGDA code. So thank you.
We have plenty of time for questions.
Hello. So there's this like standard category theory fact that if you have a right adjoint functor, say, and you say what the left adjoint is on objects, then you can automatically promote this to a functor, right?
Okay, well, sure.
You can believe me.
Yeah.
So like you can somehow inherit that functoriality from the other adjoint. So I'm curious whether this is true also for this kind of situation, that like maybe to prove the left adjoint is too coherent, it would suffice to prove the right adjoint is too coherent, and maybe that would be easier.
Yeah. Well, that's interesting. I didn't know that fact, so I couldn't say specifically, but that's an interesting idea because definitely the other side should be easier. We just need preservation of limits, which are much easier to deal with. So that's an interesting idea. Yeah, thank you.
Okay, let me know if you.
Yeah, I think I'll probably look into that.
Anyone else?
Yeah.
Hi, yeah, thank you for your talk. You in the definition of a pre-category or a wild category that you gave, you said you just remove the set condition. But what happens if you require something like the triangle and pentagon identities on the associators and the uniters? Is it then still possible for well to actually show that the composite equals the desired one?
I don't think so at first glance, because to get this specific standard proof I want to go through, we need some data on the interaction between the adjunction squares, composition law of the functor, and so forth. To me, it seems more like trying to get some pseudo-naturality conditions on the naturality squares of the adjunction. That's the two categorical data we're looking at, more than just more data on the wild categories themselves.
Okay, but so is it then incorrect to I would suspect that just by requiring these coherences on the wild categories themselves, that the functors in particular also preserve these coherences, and in that way, yeah, you would get the naturality somehow.
Okay, so you're also talking about promoting the definition of functors to preserve all that data. I still think you need some, I mean, the two categorical notion for the higher data on the adjunction would be some pseudo-naturality. So I think you need some conditions on the junction data as well, but I can't say I've formally tried it.
Okay, thanks.
Time for one more short question. Is there another online? Oh.
I've got a comment and a question.
Go ahead.
Go ahead. Yep. So the quick comment is you mentioned strongly homogeneous, but I think every homogeneous type has a strongly homogeneous structure just by post-composing by what you get at the identity.
Okay.
So just a thought that I think that's not really an extra condition. But my question, on your second last slide, you mentioned that for reflective subuniverses, you think it's more difficult to prove that they satisfy coherence than for a modality.
Yeah.
And I'm curious why there's a difference there. What's the modality giving you that you don't have in the reflective subuniverses?
The modalities, the dependent induction principle seems to make things much easier. It at least gives me a pretty easy idea of how it would go through. So that's the difference in my mind at this point.
Okay, great, thanks.
All right, let's thank the speaker once more.